Okay, 14.2 is on solution concentration. We want to look at the variety of ways in which we're going to express solution concentration, and we're going to look at the different types of calculations, and then we'll also get some practice on those calculations. Some review terms for us are going to be solvent, solution, solute, which gets dissolved in the solvent. Some new terms for us are going to be concentration, molarity, molality, mole fraction. You've probably heard me say molarity before in terms of the different solutions we were using in lab. For instance, yesterday we talked about how hydrochloric acid was 6 molar. So that means that it was 6 moles of the hydrochloric acid per liter of solution. When we talk about concentration, we're talking about different solutions or potencies of solutions. So if you look at these two T's over here in figure 4, we can see that the one on the top is going to be more concentrated than the one on the bottom. This is because the tea bags have been in the tea longer. So therefore, more of the tea oils have been able to dissolve in the water. Something with a visual color in solution is very easy to see that where one is more concentrated than the other. However, most solutions in chemistry, you'll not be able to have any indication of which one is more concentrated just by visually looking at it. Some of them, there are some colored solutions. For example, if you have copper ions in solution, it is blue, or iron ions in solution are orange. Silver ions have a grayish hue to them. So there are some types of ions that do show up as a colored feature in a solution. However, the vast majority do not. Think about maybe sugar water or putting salt in water. We can't really see, we don't have any indication of how much salt is in salt water or how much sugar is in sugar water. So we need to have different ways of representing the concentration rather than just looking visually. The different ways that we can represent concentrations are using these 5 things. We have percent by mass, percent by volume, molarity, molality, and mole fraction. And you could see that all of these, except for this molality one, are going to have something about the solution in the bottom of the denominator. And it's going to have something about, and all of them is going to have something about the solute in the top, in the numerator of the fraction there. So in most cases, except for molality, we're going to have solute over the entire solution. In other words, these are all portions of a whole. Remember that a solution is made up of 2 different components. We have the solute and the solvent. You'll recall that I previously said that solutes get dissolved in solvents, but a better definition for solute and solvent is that the solute is the substance that's present in the smaller amount, and the solvent is the substance that is present in the greater amount. So most solutions that you probably think about are going to be solutions based with a solvent of water. So we're always talking about things dissolved in water. And in this class, in chemistry labs, oftentimes that is the case because water is a good solvent for a lot of materials. So if we want to use a certain chemical in lab, we just make a solution out of it with water as the solvent. Whenever we have water as the solvent, we call that aqueous. So an aqueous solution is one that has aqua, which is water in it. So all of these we have portions of the whole. The solute, a portion of this solution. So if we percent by mass, we would look at the mass of the solute divided by the mass of the entire solution. The mass of the part that we want to analyze compared to the mass of the entire thing. We could also do percent by volume. We could do the volume of the solute compared to the volume of the entire thing, the volume of the solution. We could do moles of solute compared to liters of solution. That's one of the most common ways to represent concentration in chemistry. And then we have, I'm going to skip molality for a second. I'll go back to that. And we have the moles of solute divided by the moles, that are present in the entire solution. So the moles of the solute plus the moles of the solvent, which would amount to the entire solution. Solute plus the solvent. Molality is the one that kind of sticks out. It's the oddball, because all of them are going to be the mass, the volume, the liters, or the entire amount of moles of the entire solution. However, molality, it's dividing by the kilograms of the solvent. So molality is often used for solid phase mixtures, where maybe if we have a mixture of powders, we would use molality, because oftentimes if you have a solid-based mixture, it's going to be practical to use kilograms of the solvent, whatever the substance is that is present in a greater amount. You need to be careful with the words molarity and molality, because they're obviously they sound very similarly, and they have one letter difference. But also, the variable that we use to represent these is both M. Molarity gets a capital M, and molality gets a lowercase m. So you have to be very careful when you're denoting the difference between these two. They sound very similar, they're the same variable, they both know moles of solute in the numerator, but they both have two different denominators and they signify two different things. You'll also need to be able to distinguish between a little m for mass and a little m for molarity. So we have a shared variable m for molarity, little m for molality. You'll also recall that we used a capital M for molar mass too when we were doing the configurations of the gas law, and of course, when we're talking about solutions, we're talking about molarity or molality. When we're talking about gases, or maybe just other amounts of substance, perhaps, little m is mass, and capital M is molar mass. So you got to always be aware of the context in which you're using these things. So here are the first two concentration types. These are the percentage ones. We have percent by mass, percent by volume. If you go to the drugstore, perhaps, and you get some type of medicinal cream, or maybe you get a prescription medicine, or you get a OTC over-the-counter drug. All of these, if you look at the ingredients label, it's going to give you a percent by mass. It's going to say in this pill, in this cream, and whatever you're buying, it's 2% the active ingredient, whatever that drug may be. So if I were to get, I don't know, maybe a vitamin C pill, it's going to say, actually, it's not a good example. I think I'm going to get an antacid tablet. So I can look on the side, and it's going to give me an indication, a percentage by mass of how much of the active ingredient is in one of those tablets, and the rest of that percentage is going to be fillers and binders to make it in the tablet form, to maybe flavor the tablet. So it's going to be by mass, what percent of that by mass, what percent of that is the specific drug. That's only practical for things that are in the solid state or things that are in gels and creams. If you have something that is in the volume state, so let's say I go to the drugstore and I get a bottle of hydrogen peroxide or maybe rubbing alcohol. These are going to be expressed in percent by volumes. So, for example, if I get a bottle of the hydrogen peroxide, it's going to say it's 3% solution. That means in that entire bottle of hydrogen peroxide, it's 97% water by volume and 3% hydrogen peroxide. So hydrogen peroxide in higher concentrations is a very nasty, dangerous chemical, but when it's watered down to a 3% solution, it's useful for topical applications. If you ever go to a liquor store, or if you buy a beer or a wine, those will always be represented by percent by volume as well. So if a bottle says that it is 20% alcohol by volume, that means that it's going to have 20 milliliters. For every 20 milliliters of alcohol, there's going to be an additional 80 milliliters of water. So that would give us a 20% solution. So let's try this problem. It says in order to make a sodium chloride concentration in the ocean water, and the aquarium must contain 3.6 grams of sodium chloride per 100 grams of water. What is the percent by mass of sodium chloride in the solution? You need to be careful with this type of problem because intuitively you just want to take 3.6 and divide by 100. But you'll recall that the equation is the mass of the solution. Well, 100 is the mass of the solvent. To have the mass of the entire solution, you need to add the solute to the solvent, and then that's going to be your total solution mass. So the mass of the solute, 3.6. Mass of the solvent, 100.0. So we first add up the mass of the solution. 3.6 plus 100.0 gives us 103.6. That's the mass of the solution. We want the percent by mass of the solute, which is the chemical question. Notice we're not really concerned about the water. We're concerned about the salt content of the solution. The water is the solvent, is the chemical as the solvent, or the carrier for the chemical question. Now, the chemical question. 3.6 grams divided by our total of 103.6, and we find that the percent by mass of the solution is 3.5. When we added the mass of the solute and the solvent together, we need to be precise to the tenths. That gives us 4 sig figs for the total solution mass. However, the mass of the solute is only 2 sig figs. So when we divide to get a percent mass, we have 2 sig figs. So therefore, 3.5% is our answer for that one. So here is our molarity equation. I already mentioned this is the most commonly used concentration type used in the chemistry laboratory. And molarity is symbolized by a capital M. It starts with the 3 letters MOL because we have moles of solute in the top. So we're talking about how many moles of something in the rest. So in this case, in liters of solution. So not only are we talking about moles of solute per volume of solution, we're talking about specific units of volume. It has to be liters. If it is not liters, then it is not molarity. So oftentimes, to remind myself that I need to have liters of solution instead of this volume. So true to form, the variables would be a capital M is equal to the moles of solute. So N is the variable for that, divided by a capital V for volume. That would be the true variable format of this equation, this equality. To help me remember the units, I sometimes think about it like this. A capital M for molarity is equal to moles, I just explicitly write MOL, divided by capital L for liters. So rather than using this one over here, which is the actual format for the equality with the true variables, I use this other one, this kind of shortcut one, just for purposes to help me remember that I need to have liters in the bottom there. The units on a molarity measurement will also be moles per liter, by the way. Oftentimes in chemistry, it is shorthand to just use the unit of capital M. So yesterday we used acid that was 6 molar. So we described it as being 6 molar. What that actually means is 6 moles per liter. But oftentimes it's an acceptable shorthand to also just say 6 capital M. So all three of these mean the same thing. A 6 molar solution is 6 moles per liter, which is 6 capital M. The only true units would be that middle one, the moles per liter. We can also see that we have a dilution equation there. And this will recognize it to be similar to some of the changed equations that we've been dealing with. When we're talking about molarity, which is a concentration, the proportion would be that it's inversely proportional to volume. That means if you have a greater volume, then the concentration will decrease. If a smaller volume, then the concentration will increase. Think about this in a practical sense. Let's say that I'm going to have soup. I'm making soup. I pour the soup in the pot, and it's one of those soups where I also have to add a can of water. So I pour the can of soup, then I fill the can up with water, and I add that water as well. What if I forgot to do that? How would that change the taste of the soup? Well, the soup would be very salty. It would be highly flavored. It wouldn't have the right balance of action. What if instead of adding just 1 can of water, I added 5 cans of water? How would that soup taste? It would be flavorful, it would be watery. So as we add more volume, as I add extra water, the concentration of the soup is decreased, it's watered down. The concentration and volume of solution are inversely proportional. I would go from a proportion to an equality. We introduce an equal sign and a constant. So concentration is equal to K times the inverse of V. I wanted to solve for that constant. I can do that. So I have concentration. I'm going to see from this point on, concentration times volume is equal to that constant. These are variables, so I can have concentration 1, volume 1 is equal to a constant. Or I can have concentration 2 times volume 2 is equal to that same constant. Concentration 3 times volume 3 equal to that same constant. This constant is always the same, so therefore I could say C1 V1 is equal to C2 V2. Or if I want to deal with molarities, I could do capital M1 V1 is equal to M2 V2. And that is our dilution equation. Our dilution equation can be used if we are to take a higher concentration of something. Let's say we had that 6 molar hydrochloric acid yesterday, and I wanted to water it down. I wanted to dilute it to a lower concentration. Well, my initial stock solution of 6 molar hydrochloric acid would be condition 1. So let's say I wanted it to water it down. I wanted to get 500 milliliters of a 2 molar solution. So on the right side of this equation here, that's the solution that I want, and then the left side of that is the stock solution, the solution I'm starting with. So if I want a 2 molar solution and I want 500 milliliters of that 2 molar solution, and I'm starting with a 6 molar solution, I should be able to solve for how much of that initial 6 molar solution I would need to water down to the point of getting 500 milliliters. 500 is 1,000 divided by 6 is 166.67. I'm ignoring 6 bits. Now, I'm writing the problem. I would need 167 milliliters of this 6 molar solution diluted down to 500 milliliters to get my desired 2 molar solution. This is the purpose of a volumetric flask. This flask is designed this way. Exactly 500 milliliters. So if I wanted to make this 2 molar 500 milliliter solution of hydrochloric acid, I would need to first get 167 milliliters of that 6 molar hydrochloric acid and put it in here. Once I have it in there, I'm going to then fill it to the line, which is 500 milliliters. I couldn't just add the balance. I couldn't just subtract 167 minus 500 and then add that because it would be imprecise. And depending on the type of solution I'm making, the solutions may be more or less miscible. And there are some solutions where you can add, for instance, if I add an alcohol to water, I can add 100 milliliters of alcohol and 100 milliliters of water, and when it's all said and done, it would be less than 200 milliliters. Because the solvent molecules will actually be closer together with other solvents than themselves. So solutions are not perfectly additive in that manner. And you need something like a flask to be able to make that solution be exactly 500 milliliters. And that's what's shown down here. So, it says, accurately preparing a solution of copper 2 sulfate involves several steps. Explain why you cannot add 375 grams of copper 2 sulfate directly to 1 liter of water to make a 1.5 molar solution. So if I were to calculate, let's say I want to make a 1 liter solution of 1.5 molar copper 2 sulfate. A 1 molar solution is my desired concentration. And then I want a volume of 1 liter. So one would be able to take this molarity and say, okay, well, the molarity is 1 molar. How many moles would I need to have a 1 liter solution? So that would mean that I would have to have, to solve this, I would need 1 mole of the copper 2 sulfate, SO4, to create that solution. And if I looked at my periodic table and I added up all the masses, I would get 375 grams for the mass required. I could not simply just take that 375 grams of that copper 2 sulfate salt and add it directly to the 1 liter of water. Because as soon as I add that 375 grams of the salt to the 1 liter of water, I no longer have a 1 liter solution. I have 1 liter of water plus whatever volume that dissolved salt is going to occupy, which is going to be something. It's going to take up space somehow in that solution. I don't know how much it's going to take up, so I can't easily figure that out. So if I'm going to make this solution, step 1 would be the mass of the solute is measured and it's added to the flask. Step 2, the solution is placed in the volumetric flask of the correct volume. So I'm going to be making 1 liter of solution. So I have a 1 liter volumetric flask. I'm going to then add water to dissolve. And once it's all dissolved, I'm going to fill it directly to that line, which signifies exactly 1 liter. And that ensures that I'm making a 1 liter solution. If I add 1 liter of water to that measured out, I would end up with a volume greater than 1 liter, and I would end up with a molarity that is not what I was going for. Because if I have a solution that's greater than 1 liter, that's going to decrease my molarity. So if I was going for a 1.5 molar solution, I would not end up with that. So I need to use a volumetric flask to make that solution. So here, if you were to look at a concentrated solution like the one on the left, and then a dilute right, or a solution like copper 2 sulfate, it's very easy to see the difference. A more concentrated solution is a darker color blue. As I mentioned at the head of class, that is not always the case. You cannot always see different solutes in solution. If you were to look at the particulate level, we would expect to have more solute particles per solvent on the left than on the right. And so you could see in this little zoomed in area, they have about 5 1/4 blue solute particles, and then on the one on the right, they have 3. Showing this that the one on the left is more concentrated than the one on the right, which we can visually see as we add the water to the concentrated solution, it becomes more dilute, a weaker concentration, a lighter color. Here is another example problem. A 100.5 milliliter IV solution contains 5.10 grams of glucose. What is the molarity of the solution? The molar mass of glucose is 180.16 grams per mole. So our approach to these problems is to first write your givens and then establish what equation you're going to use. So it says 100.5 milliliter IV solution. So that means the entire solution, that's the volume. So V is equal to 100.5 milliliters. And it says it contains 5.10 grams of glucose. That is the chemical in question, that is the solute. So you have M, little m for mass, is equal to 5.10 grams. And I think it's always a good idea to tag whatever chemical you're using. So I'm going to put C6H12O6 after the grams. You know that that's the mass of glucose. And then it's asking what is the molarity. So I'm going to put capital M equals question mark. And then it gives us the molar mass. Well, we know the equation for molarity is capital M is equal to the moles over the liters. Do I have molarity? No, that's what I'm looking for. So that should be left as capital M. Do I have liters of solution? No, but I have milliliters and I can convert that. So I'm going to convert my milliliters to liters. For every 1,000 milliliters, I have 1 liter. This is effectively moving the decimal 3 to the left, and I get 0.1005 liters. That is a value I can plug in for my equation. Do I have moles? No, I don't. I have a mass, which hopefully by now you could recognize that if we have a mass and a molar mass, we could very easily convert that. Because a molar mass, in this case, 180.16 grams per mole, is a conversion factor. Or I could use the inverse, 1 mole for every 180.16 grams. For this one, I want to get rid of grams, so I'm going to be using that second one. So 180.16 grams in the denominator, 1 mole in the numerator, grams of glucose cross off, and that will give me moles, which is a value that I can plug into the equation. So 5.1 divided by 180.16, I get 0.0283. Because this is not our ultimate answer, I'm going to be plugging into a different equation. I don't want to round this. Technically speaking, this would be 3 sig figs, but I have more digits on my calculator. I'm going to take a couple more just to be sure that I'm not going to hurt my final answer. I just want an unrounded value. So now I have moles, which I can plug in. I have liters, which I can plug in. And I'm solving for molarity, so that all makes sense. Start plugging them in. 0.028308 in the numerator, moles, divided by the volume of 0.1005 liters, and that's going to give me a 0.2817 mole per liter solution. Rounding, however, I should have 4 for my volume, 3 for my moles. Therefore, I should have 3 sig figs. This is 0.282 moles per liter for the answer. So I could verbalize that as a 0.282 molar solution. So you can see here, they first solved for the moles. They got 0.0283, just like we did. They converted the milliliters to liters, 0.1005 liters. And they divided the two, and they had a 0.282 molar solution. We've got one more. Example problem 3. If you know the concentration and volume of the solution you want to prepare, you can calculate the volume of solution you will need. What volume in milliliters of 2.00 molar calcium chloride stock solution would you use to make 0.50 liters of 0.300 molar calcium chloride solution? First step, write your givens. So my knowns are 2.00 molar calcium chloride, 0.300 molar solution I want. So I'm diluting from 2 to 0.3. And of that second solution that's 0.3 do I want? I want half a liter, or 500 milliliters. So it's saying how much of that initial stock solution of the 2 molar calcium chloride solution, how much of that do I need to water down to half a liter? So when I do this, it becomes very apparent because I have 2 molarities, because I have a volume, I'm looking for a second volume, this is a change in equation. The only one that we have for this chapter so far is my dilution equation. C1 times V1, concentration 1 times V1 is equal to C2V2. And 1V1 is equal to V2. So molarity 1 times volume 1 is equal to molarity 2 times volume 2. They're going to rearrange this and solve for V1 first, and then they're going to plug in. So plug in into the equation, V2. Another way of thinking about this is, while they're saying M1, V1, M2, V2, you could also think about this as the old solution, so the original, the stock solution that you're starting with, and then the new solution on the right side. That's another way of thinking about it. So we want to know how much of the old solution we need to water down. We have the volume of the new solution. It's going to be 0.5 liters. It's going to go in as V2. We have the molarity that we're going to want for the new solution. That's M2. And then we have the molarity of the original solution, that's M1. So plug all of those in and solve. And we get 75 milliliters needed. Because this question does not ask for, it just says, oh no, it does, what volume in milliliters. So it does ask for milliliters. I was going to say, if it just asks for the volume, you don't necessarily need to convert it back to milliliters. In this case, it does ask us for that, so we would have to. But if it just said, what volume of the original solution would you need? Well, our answer comes out to be in liters, 0.075 liters. So we could have just stopped there if it wasn't specifically asking for milliliters. That's what I was going to say. So how would one make this solution? They would take 75 milliliters of the calcium chloride solution. They would put it in a 500 milliliter volumetric flask, just like the one I have here, and then they would top it off to the line with distilled water to dilute it down, water it down. We also have molality. This is the one that I said is kind of the goofy one, the oddball of the bunch. We're using the little m. This is moles of solute over kilograms of solvent. So here's an example problem. Student adds 4.5 grams of sodium chloride to 100.0 grams of water. Calculate the molarity of the solution. Oh, molality, I even misread it. Molality of the solution. So Whenever you have a word start with mole, so molarity or molality, it's always going to be moles of the solute divided by one thing or the other. Molarity is dividing by the liters of the entire solution. Molality is dividing by the kilograms of just the solvent. So molality equations are actually fairly simple to solve. We just need to convert our solute to moles, and then we need to convert our solvent to kilograms. So our knowns, we have 100 grams of water, 4.5 grams of sodium chloride. Looking at these, the water is present in the greater amount. That's clearly the solvent. And then we have the sodium chloride is 4.5 grams. That is the solute. We want moles of solute. So 4.5 grams of sodium chloride divided by, and then you could determine the molar mass of sodium chloride. Look on the periodic table, 1 sodium, 1 chlorine, adds up to 58.44. We get 0.077 moles of sodium chloride. That's going to go in the numerator. Then we also need kilograms of solvent in the denominator, 100.0 grams. 1,000 grams for every 1 kilogram, so we're effectively moving the decimal 3 to the left when we go from grams to kilograms, and we get 0.1000 kilograms of water. Moles of solute in the numerator, kilograms of solvent in the denominator. We just need to divide these. And we get 0.77 moles per kilogram. Because our mass of the mass of the sodium chloride is reported to 2 sig figs. Our moles were reported to 2 sig figs, and when we plug that in, that's going to limit our answer. So 0.77 should be 2 sig figs moles per kilogram. And the last type of concentration that we're going to talk about is mole fraction. Mole fraction is the number of moles of whatever substance is in question divided by the total number of moles present in the mixture. So mole fraction, we use the variable x. So x sub A on the left is the mole fraction of chemical A, or substance A. The mole fraction of substance B is x sub B. So if we were to add these two mole fractions up, they ought to add up to 1, because fractions that are parts of a whole should always add up to 1. Think of it like a pie chart. So here we have a hydrochloric acid solution. It's 78% water and 22% hydrochloric acid. So therefore, I would say that the mole fraction of hydrochloric acid was 0.22, and the mole fraction of water was 0.78. So this is percentage by moles. If we were to do the percentage by volume, we would expect it to be different. If we were to do the percentage by mass, we would expect it to be different. Percentage by moles, we need to have the mole values first. Okay. I do have example problems on the worksheet. Let's go ahead and load up this 14.2 solution concentration study guide. This is our in-class assignment, and we also have our homework assignment, 14.2 concentration and diluting worksheet. I want to do 17 together. This is a mole fraction problem. It says calculate the mole fraction of hydrochloric acid in an aqueous solution that contains 33.6% hydrochloric acid by mass. Show all of your work. So if it's 33.6% hydrochloric acid by mass, our key word here is aqueous. That means that the rest is water. So if we take 100 minus 33.6, we're going to get, whoops, mistype, 66.4. Whoops, I'm typing in the wrong place. 66.4% water, H2O. So we have 33.6% hydrochloric acid by mass, 66.4% water. So I'm writing my Gibbons. This is the, why is that black? This is the tricky part right here. How do we get from percentages to moles? The way that we're going to do this is we're going to assume a sample size. That is, I'm going to say that I have a 100 gram sample, and if I have a 100 gram sample, that would mean that I have a 33.6 grams of hydrochloric acid in that sample. And that would also mean that I have 66.4% or grams of water in that sample. If we have masses, we could get moles. Make these 1. With a molar mass, we can convert these to moles. You might recall the molar mass of water because we've used it so many times at this point. It's 18.02 grams for every 1 mole. So this will give us the moles of water. On my calculator, 66.4 divided by 18.02, I get 3.685 moles of water. And for the hydrochloric acid, I have hydrogen and chlorine. Hydrogen is 35.45, if I'm not mistaken. Need to double check here on the table real quick. 35.45. Hydrogen is 1.01. So when we add these up, I'm going to have 36.46 grams for every mole. Do the same conversion that I did with the water. 36.46 grams for every 1 mole. And then on my calculator, 33.6 divided by 36.46, I get 0.92, and we'll round this to 2.922 moles of hydrochloric acid. So now that we have moles, we can now get mole fraction. The mole fraction, so the X sub HCl is going to be the, the moles of HCl divided by the moles of HCl plus the moles of water. Moles of HCl was 0.922 moles. of HCl divided by 0.922 moles plus, so the moles of water is 3.685. 3.685 moles. So on my calculator, 0.922 divided by left parenthesis 0.922 plus 3.685, right parenthesis, enter. I get 0, and I kept, so I need 3 sig figs due to the percentage way at the beginning. 0.200. This is unitless because I have moles and moles. Moles on the top, moles on the bottom, they cross off. This is just a percentage. So what this is saying is that the mole fraction of hydrochloric acid is 0.200. It asks to calculate the mole fraction of the hydrochloric acid. That's what we did. To calculate the mole fraction of the water, we would just swap out the moles of hydrochloric acid with 3.685 moles of water, and we'd solve it and we'd get 0.800. So 20% hydrochloric acid, 80% water, if we're just looking at the moles. All right. All the other ones are easier. So go ahead and work on that. Submit when you're finished. And that is it.